Great, let's get started. So welcome back. This is the second tutorial session of Advanced Social Psychology and Judgment Decision Making. So in this tutorial, we're going to talk about effect sizes, confidence intervals, and power analysis. And today is me, Qinyu, speaking, the only tutor that hasn't spoken for the tutorials. And I'll be responsible for the 2 tutorial sessions in this week. And this is my first time teaching, so there could be issues. So I appreciate that whenever there is an issue, just interrupt me. If I say something unclear, feel free to interrupt me or ask questions in the chat box. So the first half of the tutorial is going to be more technical. I'm going to introduce the concepts of this stuff, and the second half is going to be more practical. We're going to use Javuvi, G-power, and R to calculate effect sizes, confidence intervals, and conduct power analysis. So this is today's agenda. First, it's going to be an introduction to the new statistics, and the second half is going to be about power analysis. So effect sizes and confidence intervals are collectively referred to as the estimation-based statistics. They're by no means new. Statisticians have them long ago, but they are new in the sense that psychology and many other disciplines rely predominantly on what we refer to as p-values. And that reliance is problematic, as we all know, and we're going to revisit that. So we start from the fundamental question, that is, what do we want to know when we conduct empirical research? Whether we do that research because out of curiosity or out of some monetary motivation, we want to know in the end is that what we want to know is that is our hypothesis true? And because the world is probabilistic, we can never know anything for sure. We want to know how likely is our hypothesis true. And even if we don't have a hypothesis, suppose that we are conducting an exploratory research and we have the data before we have any hypothesis, we still want to know whether there is something in there versus there is absolutely nothing of interest. So this is the fundamental question that we are interested in when we do empirical research. But this is not something p-values tell us. So first of all, p-values do not tell us the probability that the alternative hypothesis, or H1, is false. So suppose I conduct a study comparing 2 groups. I get a p-value of 0.03. That's a significant result, a significant difference. But it does not mean that the alternative hypothesis, the probability that the alternative hypothesis is false is 0.03. And similarly, this also does not mean that the probability that the null hypothesis is true is 0.03. You remember that the null hypothesis is there's no difference. What p-values tell us is the probability that we obtain the data that we have at our hand, or more extreme data, given that the null hypothesis is true. So if you are familiar with probability notation, here's what p-values tell us. The probability of our data given the hypothesis, given the null hypothesis in particular. This vertical line here means conditional probability. So we assume that the null is true and we have the probability of our data or more extreme data, and that's what p-values tell us. However, what we want to know is actually the reverse. We want to know the probability of the hypothesis, regardless of it's the alternative or the null, given the data. So we want to know how likely is there a difference and how likely there isn't any difference based on the data we have. So p-values don't tell us what we want to know, and there are other drawbacks of p-values. And first, p-values do not allow us to make comparisons between study results. It's simply not right to say that a p-value of 0.01 is more significant than the p-value of 0.1. This is a wrong comparison that we're making here. because we only declare those results with a p-value under 0.05 as significant result, and we only declare those results with a p-value over that value as non-significant results. But we cannot compare them in terms of their significance. And there's a famous saying about this, is that statistical significance does not imply practical significance. And we will come back to this point later. And also, as you might know, that p-values encourage what is called dichotomous thinking. It forces us to classify our results in terms of those that are significant and those that are non-significant. But if we think about it, is there any substantial difference between a p-value of 0.0449 versus a p-value of 0.051? Likely not, because we can get these two p-values just by including or excluding one data point. But one result is declared as statistically significant and the other is statistically non-significant. So p-values are not enough. And by doing research, we want to know if there's a difference, how large the difference is between the two groups, or how strong the relationship is between two variables. Like how large these two distributions differ from each other and how closely these two variables co-vary. We need information about these magnitudes, so we need a measure for them. We keep talking about effect sizes since the beginning of the courses, the beginning of the very first lecture. But what is an effect in the first place? Effect is a very general term that we're talking about here, which describes the influence of one variable on the other. So in the case of group difference, we're talking about the effect of group on some dependent variable. So suppose I want to see if there's a height difference between two genders, between males and females. I go out and test these hypotheses with some subjects that I recruit, and I see there's a difference. So what I observe is an effect of gender on height. And in the case of regression correlations, the effect actually refers to how much the predictor or predictors can predict an outcome variable. But be cautious here that this effect, although the word effect seems to imply a causal relationship, it actually does not. As we all know, that correlation doesn't imply causation. So for example, suppose we observe a positive correlation between parents' socioeconomic status and children's height. This does not mean that the parents' socioeconomic status have a direct effect on a causally influenced children's height. It may be because the parents are rich, because the parents know how to take care of their kids, the children get higher. But that does not mean that it's the direct causal relationship between the two variables that we're examining here. So now we know what effect is. What can be a metric to quantify the difference between two groups? Say where we're trying to quantify the difference between two groups. And a most straightforward measure for the difference between two groups is just the difference between two group means. So suppose I have an intervention to boost students' academic performance. And so I test this intervention in some students, and I get a control group and I get a treatment group. I administer this intervention to the treatment group, and we observe that the treatment group has on average 0.25 GPA increase after the intervention. So if we look at the two graphs on the right, in both cases, the treatment group has a higher average GPA than the control group. But in the case in the above, the overlap between the two distributions is smaller than the overlap in the graph that's below. What that means is that if we randomly draw a student from the treatment group here, and we randomly draw a student from the treatment group and from the control group here, and we compare them. If they come from the below study, the study below, if they come from the study above, it's more likely that the treatment student is going to have a higher mean than the control student. In other words, we can obviously see that the effect size in the above is larger than the effect size in the below. So it seems that raw mean difference is not a good measure for effect sizes. And we still have to consider the case when we have a different measurement scale. So in Hong Kong U, we have a GPA system where the maximum is 4.3, sorry. But in the US, the maximum GPA is 4. And in Germany, they have a 1-6 system where the 1 refers to the highest score. So what shall we do if we want to examine the effectiveness of the varying intervention if we administer this intervention in some German schools or in some US schools? We still have some letter grades here. How do we compare how do we see if the effects are the same or not? So basically, we need measures that allow us to compare the magnitude of effects across contexts and studies. And that's why we need standardized effect sizes. We need standardized effect sizes because we want to take into account a sample dispersion, like here. We want to take into account how wide the distribution is. We also want to standardize effect sizes because they allow us to compare across studies. So we can roughly compare the standardized effect size measures with the international system of units. We have we now have the international standard of using, say, kilometer to measure the length, so that we can compare. So everybody knows how to measure the length of an object. But some countries still use miles, and that's why we cannot directly compare length with them. We cannot directly compare the numbers of length if we happen to meet someone that living in those countries. So we need to differentiate between effect size and effect size measures. So think of effect size as a number, as a magnitude, and think of effect size measures as the units that I'm presenting here. And one of the most widely used effect size measure, standardized effect size measure, is Cohen's d, which is named after this man here, the famous statistician and psychologist Jacob Cohen, who is also the founding father of estimation statistics that we are all talking about here, that we are sitting here to study. So basically, Cohen's d is the main difference between two groups divided by the pooled standard deviation. You don't need to remember this formula because we will never calculate by hand in this course. But this is the most widely used standardized effect size for group differences. And there are other similar measures such as Hedges G and Glosses delta. We need to choose what to use depending on the context. So people come to Cohen asking, what does Cohen's d mean? What does a Cohen's d of 1 mean? Can you give us an interpretation on what these numbers means? And Cohen was very reluctant to that because he thinks that the evaluation interpretation of effect sizes should be based on the specific context in which the research is conducted. So I suppose, so if we set that the small effect as a Cohen's d of 0.5, it might be the case in social psychology, but it might not be the case in cognitive psychology, in neuroscience. So that's the reason why Cohen was very reluctant to give such benchmarks to help people to interpret what this measure mean. But people insist that we need a guideline, so you must give us a guideline since you're the person who propose it. So Cohen, okay, you want a guideline, then let me propose this guideline. So I will propose that Cohen's d of 0.2 is a small effect, a Cohen's d of 0.5 is a medium effect, and a Cohen's d of 0.8 is a large effect. So you can have a basic visualization here on how large the difference is between two groups to qualify as a small effect based on Cohen's standards. And this is a median effect, and this is a large effect. And similarly, for correlation, we just have the correlation coefficient R that we report for correlation as standardized effect size measure. So basically, it quantifies how strongly two variables covary for Pearson correlations. This man is Carl Pearson, one of the most important statisticians in history. And Pearson's correlation is used for two continuous variables following certain distributions that I'm not going to illustrate here. Basically, this is a small correlation coefficient, and this is a median correlation coefficient, and this is a large one, just like the benchmarks that we see here. These are traditional or conventional benchmarks that these statisticians propose just for guiding people's expectations about effects. But it turns out that these benchmarks may not be accurate in terms of reflecting the real effects in psychology, and real psychological effects actually turned out to be smaller than what Cohen has proposed. So in this 2003 meta-analysis, these researchers quantify, like they search many articles in the published literature, and they conclude that it indicates that correlation coefficient of 0.1 is small relative to most social psychological effects, and a correlation which is the same as this one actually. But the median effect, they say, it indicates that the correlation coefficient of 0.2 is a median-sized effect, which is actually smaller than the median effect by convention. And they conclude that a correlation coefficient of 0.3 is large relative to most social psychological effects. Less than only a quarter of the mean effects are large in the published literature, which is also smaller than the large effects here. And we also have to consider publication bias, by reason of which the published effect sizes tend to be larger than the real effect sizes, which we'll come back later. And there are other various effect size benchmarks, as you can see here. Later studies also use a similar approach to examining the effect sizes that are reported in our published literature. And basically, they are very similar, close to what this Richard and L found. So, but just make sure that you know that this is for social psychology only. If you are studying cognitive psychology or neuroscience, it's likely to be different. So that's why Cohen was very reluctant to propose a general benchmarks, which doesn't really make sense, because we have to consider the study that we are the field that we're working in. And for categorical variables or discrete data, we also have their own standardized effect size measures. And one of them that is most widely used is the odds ratio. So odds is the probability that event A happens over the probability that A does not happen. And odds ratio is simply the ratio of two odds. And odds ratio quantifies the association between two events. To illustrate, suppose we have an intervention to help smokers to quit smoking. So I recruit a bunch of participants. I administer the intervention to some of them, and the other is going to be in the control group. And I find that for those who received the intervention, there are 48 of them who successfully quit smoking. There are 26 of them who didn't quit. And for those who did not receive intervention, 24 of them successfully quit smoking, but 43 of them did not quit. So what's the odds for a person to quit smoking when he or she receives intervention? The odds is 48 over 26. What's the odds of the person quitting smoking when he or she does not receive intervention? The odds is 24 over 43. With a bit of transformation, we can see that the odds, we get this odds ratio here, and with a bit of transformation, we can see that the odds ratio is just we multiply these two values on the diagonal and divided by these two values on the other diagonal, and we got an odds ratio of 3.31. So this odds ratio basically means that the odds of successfully quitting smoking given the intervention is 3.31 times the odds of successfully quitting smoking without intervention, which suggests that our intervention actually works to some extent. So basically, an odds ratio of 1 means no effect, or that the two events are independent. So the event of quitting and the event of receiving intervention on that are independent from each other if we get an odds ratio of 1. So so much for standardized effect size measures. There are actually multiple of them that I don't think we have time to go into everyone in depth, but I have we have this guide here that we composed, everyone composed to illustrate what these different standardized effect sizes are. So like here, we have, when we compare group differences, we have Cohen's D, Hedges G, and Glasses delta. When we use counts and proportion, when we deal with discrete data, categorical data, we have phi coefficient parameters B, Cohen's H, and many others. And when we do ANOVA, we have some others that I think are illustrated quite clearly here. So you have to choose the right standardized effect size measure for your test so that people can know that what that means. And whenever you're sure, feel free to consult here. And if you find out any mistake, you are very welcome to make your own contribution. Just go directly to correct them, because this, as everything in this course, everything is collaborative. So students are very welcome to identify the issues and contribute their own knowledge. So much for effect size. Let's go back to the slides, and we want to discuss confidence intervals. Drink some water first. So, like p-values, confidence interval is not very intuitive to understand. And many experienced researchers make mistakes in terms of understanding and interpreting confidence intervals. We may start from an example. So imagine that Philly is conducting a study. The course instructor is conducting a study, and he's examining if taking part in his courses increases the student's overall GPA in psychology, which we hope is the case. He collected some data from students, from those who attended and from those who did not attend, and found that those who took his courses had GPAs that were on average 0.25 higher than those who did not. And this and the confidence interval is this is an unstandardized effect size, just to make sure. And the 95% confidence interval for this unstandardized effect size is 0.1 to 0.4. So he's wondering, it's nice to know this, but how do we interpret this? So now I would like to invite you to go to Menti to use this code and to answer the questions here. That how do we interpret this confidence interval? Hope it works. Nobody's responding. Is it working like Kit? Oh, we get one response. So this person thinks that if we were to repeat the study over and over, then 95% of the time the true GPA difference falls between 0.1 and 0.4. Let me read out the options. So the first option says, if we get this confidence interval, there's a 95% probability that the true GPA difference lies between 0.1 and 0.4. And the second option reads, we can be 95% confident that the true GPA difference lies between 0.1 and 0.4. And I just read the option 3, and the last two options are I'm not sure, and none of the above. So let's see. We have 19. We have I think 16 students here. If maybe let's wait for more responses. 8. We have 8 now. 9. Okay. It seems that the majority of you choose the option 3. If we were to repeat this study over and over, then 95% of the time the true GPA difference falls between 0.1 and 0.4. Oh, we got a response from here. Actually, that's a multiple response question. So it means that it's not necessary there's only one option that's there. That's correct. All right, let's stop here. Let's just don't waste more time on this. So we have the majority of you choosing this option, thinking that if we were to repeat the study over and over, then we'll have 95 if the mean lies between 0.1 and 0.4. Is this correct? Actually, this is not. So let me begin with the correct interpretation. The correct interpretation is that if we were to repeat the study over and over with different students, then 95% of the time, the confidence intervals that we get from these repetitive studies will contain the true difference. So this person says, this is how you should interpret your results. So basically, it says nothing about the true mean difference, this interpretation. So how do we understand this? It's good that we understand this with some visualization here. So I strongly recommend this website to you, which has a bunch of interesting and interactive visualization, which help you to understand the many statistical concepts and phenomena. So interpreting this is not the one. Interpreting confidence intervals and interactive visualization. So slightly here, we adjust the significance, the confidence level that we want to have for the calculation. So suppose I want 95% confidence interval, as in most cases we rely on such a value because our alpha value, which we will discuss later, is set at 0.05. So in most cases, we calculate 95% confidence intervals. And this website uses some code on the background to generate random data which follow a certain distribution. And this distribution has a true mean of 0. And suppose we sample 20 subjects each time. And let's see what will happen if we resume this sampling over and over. Let's increase the speed for a bit. So as you can see, because our word is random, we don't always end up with the same result. In support of our to catch the true mean difference. So some of the sample will have a higher sample mean, and some of the sample will have a lower sample mean, and the important thing here is that, as you can see here, some of the confidence interval is not going to cover the true mean, which is 0, just by random chance. If we get a sample mean that is that deviates large from the true mean here, like this one, let me pause. Then the confidence interval associated with this sample mean estimation is not going to cover this true mean. And if we look at here, this CI coverage, this number indicates how many of the confidence intervals, how many of these confidence intervals that we so far generated have covered the true sample mean. And you can see that around 95% of them actually covers the true sample mean. And the number is 233, and the 14 confidence intervals miss that. So the confidence interval does not have anything to say about the true mean that we are trying to see here, but in the Menti that we just used, it actually says something about the true mean. The true mean is a fixed value. So the first thing that we need to make sure is that the true mean is a fixed value. It does not change. So it's either falls between 0.1 or between 0.1 and 0.4, or it does not fall into that range. So there's nothing we can say about the true mean. This statement sounds as if the true mean is a variable, which it is not. And let's start with the first statement. So the first statement says that there is a 95% probability that true GPA difference lies between 0.1 and 0.4. As I just said, the true mean is a fixed value. It does not vary regardless of how many samples we draw and how many sample means we calculate. So we cannot say anything probabilistic about the true mean. And also, this second statement states something about the true mean, which we can never say about it. And whenever we are trying to say that the true mean has anything to do with any particular confidence interval that we have obtained, then that means we're wrong. I hope that's clear. It's a very tricky concept. I don't think I did my best job to illustrate, but hope that's clear. But if it's not clear, I definitely ask questions. So I hope to make this very clear that we are interpreting confidence intervals right. So the correct interpretation says nothing about any particular interval that we are obtaining in our studies. But if now let's consider this question: if any confidence interval says nothing, any one confidence interval says nothing about the true mean that we're trying to see there, why do we need to provide this in our results? Because confidence interval provides information about how precise our point estimate, which refers to the effect size, is. So let's look at these three studies on the right. So the first one has a very narrow confidence interval and a low effect size, which is very close to 0. The second study has a much larger effect size. This is obviously not, well, may not be a standardized effect size, but just to make sure that the second study has a much larger effect size compared with study 1. However, the confidence interval is also much wider than this one. And the third study has a medium effect size estimate. Its confidence interval is also relatively narrower than the CI of study 2, but it's wider than that of study 1. So the one thing that we have to remember is that whenever a confidence interval covers the 0, the null hypothesis, the value reflective of null hypothesis, the result is a non-significant one. So we have a non-significant result here in study 2. And in contrast, study 1 and study 3 both have significant result. However, even if we get a large effect size in study 2 here, if our CI, our confidence interval, is not narrow enough, we cannot reasonably convince others that I've found a reliable effect instead of one that's just that we get just because we are lucky. So this one, you can see that this interval even spans into negative values, which means that if we conduct this study again, the point estimate is going to vary a lot relative to if we conduct the study 1 again or conduct study 3 again. However, if this effect size is reflective of the true effect size, then this study has revealed a bigger effect than this study has. So in terms of practical significance, if this is the real effect that's there, then this study has revealed an effect that's of bigger practical significance than this study has revealed. However, statistically, this study's results is not significant. So you can see that there's a gap, there's a dissociation between practical significance and statistical significance. And statistical significance does not mean that the effect is practically significant, as you can see here. Even it's a reliable effect above 0, like the one group is always larger than the other, but given that the effect size is so small relative to the others, it might not be very meaningful if we build on this effect to plan further studies. So that's it. That's it for confidence intervals. Any questions so far? So if you happen to have any questions, just ask them in the chat box, or feel free to unmute yourself and speak up. And the supporting tutor is gonna likely to answer the question. So after confidence interval, we'll get to power analysis. So first, power. The basics of power. Power is the probability for one study to detect an effect given that it is there. So there is an effect, there is a difference between two groups, and the probability that my study is going to detect this difference. And by detection, we mean we get a statistically significant result. We are very familiar with type 1 error and type 2 error, and this picture I borrowed from Phyllis' slides. So type 1 error is a false positive that we declare an effect to be existent when there is actually no effect. And the type 2 error is a false negative in the sense that there is an effect. However, we declare that there is no effect. So the probability that we make a type 1 error, which is also referred to as type 1 error rate, is alpha. And the probability that we make a type 2 error is referred to as beta. So power is 1 minus beta. There is an effect. That's the assumption that we have when we discuss type 2 error. There is an effect, and the chance that we miss it is beta. The chance we have it is then power. So it's 1 minus beta. And then what determines the power of a study? So first is the true population effect size. Actually, I'm going to use visualization to help you to understand all these factors that can influence the power of a study. So this is the visualization that we have, which is beautifully made and very intuitive. So we want to solve for power. We want to know how powerful the study is given all these factors. And this is the effect size, how different these two distributions are from each other. This is one group. Suppose this H0 means no difference. So we suppose the first group is the control group, so it has no difference. And this group is the experimental group, and is indicative of the alternative hypothesis. And this dark blue area here is reflective of the rate of type 2 error. So if we happen to, first I think we need to clarify that this is not the distribution of our raw numbers. It's the sampling distribution. So if we repetitively sample a bunch of subjects from the population, and we calculate the means for each sample, and we distribute this mean, and we're going to have, if we plot these means onto this graph, we're going to have this sampling distribution. So each number here is reflective of a mean instead of a raw score. So if we happen to observe a mean from the experimental group that falls in this area, this dark blue area, because the difference we have is below the critical value here, we are not going to reject the null hypothesis, but there's a difference, so we made a type 2 error. So this area, the size of this area is reflective of the type 2 error rate, or the beta rate. And these red areas here is reflective of the type 1 error rate. Because if we actually there is no difference between the two groups, and we sample one group from here, we sample another group, we sample another group from the same population, because there's no difference. So there's only one population, but accidentally we get a sample whose mean falls on this area. Because once goes over the critical value, we're going to declare that the result is a statistically significant one, and we reject the null hypothesis. But actually, that's a false rejection. So we made a type 1 error. So the size of this area is reflective of the type 1 error rate. So now let's see how our power is going to change given the change in the actual effect size between the populations. So if we decrease the actual effect size, it means that the two distributions are going to come closer. And you can see that the critical value remains unchanged. However, the dark blue area increases. Dark blue area increases, which means we are more likely to make a type 2 error. Yeah, more likely to make a type 2 error. That means we have less power. And in contrast, if we increase, I really like this animation here. It's very beautifully made here. If we increase the effect size, it's very unlikely that we're going to draw a sample from here, and instead, so as a result, our power is increased. So now we get that the power, the higher the population effect size or true effect size is, the more power we have. Other things unchanged. And sample size. Now we have we're still going to use this illustration here. This visualization here. Suppose we have a true effect size of 0.4. Now, what will happen if we sample more subjects or less subjects? So suppose we sample more subjects. As you can see, the sampling distribution is going to be slimmer and slimmer as we sample an increasing number of subjects. The dispersion is going to decrease, which means that like the more subjects we sample, the slimmer these distribution is going to be, which means that the area here is also going to decrease. So the more subjects we have, the more power we have as well. In practice, because this is the most the easiest factor to change when we want to change the power of a study. So basically, when we say we want high power in a study, we basically means we want more. We want a larger sample. We want more subjects because we cannot change the true population effect size. We cannot change the alpha value, which is conventionally set at 0.05. If we have determined on the study design, we cannot easily change that. So the only factor that we can easily change after everything else is determined is just a sample size. So basically, in practice, whenever I say we want higher power, it basically means we want a larger sample. And alpha level, this is a bit tricky. So suppose we have 40 subjects per group and an effect size of 0.4. What will happen if we increase or decrease the significance level? Suppose we increase the significance level. It means that the critical value is going to decrease, and we have more red area, but we will have less blue area. So if we increase the significance level, our power is actually going to increase. And if we decrease this significance level, our power is going to decrease. And you can see that it's actually a trade-off between these two things. It's a trade-off between type 1 error and type 2 error, such that whenever other things unchanged, the more type 1 error we have, the less type 2 error we have. That means we have higher power. So there's a trade-off there. And this usually doesn't matter unless you're working in some specific fields. So suppose you're working in neuroscience, they normally set a very strict alpha level far below 0.05 because they don't want many false positive. They put people in the fMRI scanner and they scan a large number of neurons, voxels in particular, and they compare many voxels. So these great number of multiple comparisons is going to make type 1 error more probable. So they want to limit their alpha level so that they will make fewer type 1 error in those kind of studies. But in social psychology, we normally just follow the 0.05 conventional value. And finally, statistical test study designs. We know it's the fact that one-tailed tests have more power than two-tailed tests, which we can also see why here. So everything's unchanged. We return, we keep the 0.05 p-value, alpha value, then we sample maybe 30 subjects per group, and the true effect size is 0.4. So let's see what will happen if I change from the two-tailed test to a one-tailed test. If I change this, the critical value to declare statistical significance is actually going to decrease because we're putting all those red areas here into here. So there's only one tail remaining, and the other tail, we don't care about the other tail. So we're going to have more power in the case of one-tail test instead of when we have two-tail test. And within subject designs, it's going to have more power than between subjects designs. This is because if we adopt within subjects design, it means we can parcel out the between subject differences, the differences between the individual differences between the subjects, and the effect, if it's there, is going to become more apparent, more obvious than compared with in a between subjects design where we cannot parcel out the individual differences there. And parametric tests are more powerful than non-parametric tests. The test we conduct just now, that we see just now, the t-test, the ANOVAs, the correlations are all parametric tests in the sense that they assume some distributions in the background. But now the non-parametric tests don't assume any distribution in the data. I won't go deep into that, but just so you know that the parametric tests are more powerful. So whenever possible, if you have continuous data, if your data satisfy the assumptions for parametric test, always use parametric test instead of non-parametric test, because you're not going to miss, you're less likely to miss any significant results. So that's all about power. Now we come to power analysis. Actually, when we refer to power analysis in this course, the power analysis that we're referring to is a priori power analysis, which means the power analysis is conducted before we collect any data. And there are various other kinds of power analysis that are given different names, which we will see later. But basically, they just vary. Vary in the sense that one of the parameters is unknown, and we know the other parameters, and we want to know we want to determine the unknown parameter. So in the case of a priori power analysis, we know that what effect size we're targeting. We know our design and statistical test. We know our alpha level, and we know what power level that we want to achieve. And our goal is to determine how many subjects we're going to need for this particular study. Yeah, that's a priori power analysis. And since the first lecture, Foley has emphasized that it's very bad that we have low power in our literature, in our study, but which unfortunately is the case until even now. Like many studies still continue to have low power, but we must know what's bad about having low power. So the first thing that's bad about having low power is that low power leads to more false positives and false negatives. The latter half may be easy to understand because we have low power, we're more likely to miss results, which means that we will have more false negatives. But why do we have more false positives by having low power? Illustration is always with visualization is always the better thing that we have, that we shall try. So because we're talking about false positive, that means the true effect size is 0. Now, suppose we have low power, which basically means we don't have many subjects there. We don't have many subjects there, like 20 subjects per group. Sometimes we're going to draw a mean here, and sometimes we're going to draw a mean here. Because we don't have many subjects, our sample is not going to be representative of the population that we're trying to investigate. So if we draw a sample here and its mean falls on here, and if the other sample falls here, and likely there's a difference, statistically significant difference between them, even though they're sampled from the same population. So if we do this study again, perhaps they're going to change position, and this experimental group that we think is examining a different population is going to be drawn here, it's going to fall here, and the control group is going to fall here, and it's creating a difference in the other direction. So it's also creating a false positive, but it's a false positive in the other direction. So you have a sense on why low power increases false positives, because the sample is not going to be representative of our population, and it's more likely that we're going to get extreme estimates of the sample means. And and low power also results in overestimation of effect sizes. So if we have low power, and there's a difference, suppose it's a median effect size by Cohen's benchmark. If we have low power, watch this. Watch how large a difference I need. Suppose I always get a control group mean at 0. You need to watch how large the difference we need to have to declare statistical significance. So if we decrease the sample size, you can see that the fewer subjects we have, the criteria to declare statistical significance is going to increase. Look at this value here. So now we need like a mean difference of around 0.62 to declare statistical significance. But if we have a larger sample, we only need 0.4 to declare statistical significance. And we know that only because of publication bias, only statistically significant results are more likely to get published, which means in the literature, if the studies are underpowered, the more likely that our effect size estimation is going to fall above our effect size estimation is going to be larger on average than if we have enough power, because with enough power, all these values can be declared statistically significant. So that's the reason why low power can result in overestimation of effect sizes. And of course, since we have more positives, more false positives, more false negatives, and overestimation of effect sizes, it's going to undermine the replicability of results. So overall, low power is bad, and we should, whenever possible, make sure that our studies are powered enough. And why do we need to do a priori power analysis? We need to use our resources wisely. For every research, our time is limited, our money is limited, and we don't want to waste taxpayers' money unwisely. So by determining a required sample size before we do the study, we don't have to collect many subjects more than what's needed. We will not collect fewer subjects than what needed. So we don't want to miss an effect. We don't want to spend our resources on extra subjects that are not needed. I really need to drink some water. So, and also, we also have to convince others that we have used resources wisely. So when we, if we conduct an a priori power analysis and we submit our research to the journals, the reviewers can see that we have planned our studies wisely, so that the effect that we have can be trusted, can be reliable, and they have a sense of how much power that we have in the studies that we have conducted. And that's going to help for us to produce reliable results. And that's basically the part about power analysis. And here we're going to have a 5 minutes break. And after this, we're going to do a demonstration on how to calculate effect sizes and confidence intervals in R and do power analysis in R, Jamove, and G power. So 5 minutes break. If any questions, just post them in the chat box or open your mic so that we can directly communicate. Okay, so back to our tutorial. Now, I'm going to demonstrate how to calculate. So first, how to calculate effect size and confidence intervals. Because we have limited time, we're only going to demonstrate independent samples t-test, and all the other tests, and not all the other, but most other common tests are covered in the guide, and always very detailed, hopefully detailed code that you need to do, what you need to do to calculate the effect sizes. So I will just use independent samples t-test as an example in our illustration here. As you can see here, we can calculate Cohen's d from means and standard deviations. We can calculate d from means and standard errors, and depending on the what you have, you can have many options to do the calculations. Comparison between two independent groups. So now we open the R here. So when you open R Studio, R as a, maybe I will have to start from what R is, because from the survey that we had at the beginning of the course, it seems many of you do not have experience working with R. So first thing first, in these courses, we strongly recommend you, we encourage you to do R instead of SPSS, Excel, even Jamove in G-Power, because this is the future of doing research. This is the future of using open source, open reproducible tools to conduct research. And because R is free and it's in continuous development, that means this is not a final version. It's updated much faster than SPSS is. And if you get familiar with that, you will find that this is more intuitive than SPSS or other point-and-click software is. So basically, whenever possible, try to use R instead of the other things that you mentioned in the lectures and the tutorials. So this is the interface of R Studio. We have a toolbar. We have a script, R script here, which basically is a text file of many lines of code. We have our console here, where we can type one line of code each time, and we get the result. We get the output each time after we run that line of code. We can have we have this environment interface where all the variables that we have are stored, are displayed here, and this window is have some other functions. For example, if you ask for help, suppose I want to know how does the t-test function works. So if I type in this, it will display a guide on how to use the function. And this is going to be, if we generate a graph, this is going to be where the graph displays, and the packages that we have in this on this computer. Oh, okay, it's not here. The packages we have in this computer and plot. So, sorry, this is where the plot is going to show. Now we try to. I'm going to demonstrate how to calculate the effect size for an independent samples t-test. So first of all, we generate some random data. this is a function for generating random data that you don't have to load or remember because you're not working on simulated data. You're working on simulated data not generated by R but by Qualtrics, the survey platform that you're going to use for your replication extension project. So basically, what I do here for these lines of codes, I generate some random data so that we can have our further analysis on. So that we can have our further we can analyze this set of random data. So now we have two groups, group 1 and group 2, and we have some data points here. And if we describe this data, right, this is something crucial for those who don't have the experience in R. Why R is powerful is because of the many packages that people develop to fulfill certain functions. And one of the important packages that we use is the PSYC package. If you don't have this package, I suppose if you just download R or R Studio, you don't have any packages other than those that come with R. So you have to install the packages. So you type install packages, and you indicate that you want to install PSYC, and you run this line of code by pressing enter. I already have this package, so it doesn't display anything. But if you run this code, the R will help you to install the package PSYC. And now, after you install package PSYC, you're going to have to load it. To run codes in the R script, you can either select it and run here. Now I load the package PSYC. Alternatively, you can also put your cursor here and press Control and enter. If you are on Mac, then you press Command plus enter, and then you load the package PSYC. And in PSYC, we have a function called describe by, which describe the data according to their group. And now, after I run this line of code, I get this descriptive statistics by group. So you can see that the mean of group 1 is 17.85. I note it down here. The standard deviation is over 70. The mean is 70 here, and the standard deviation is 95. So now we run this. We conduct this independent samples t-test on the data that we just generated. The result is going to indicate that it's a marginally significant difference between the groups. I have a t equals 0.966. And the degrees of freedom is 38. Okay, here we've got the statistics that we need to calculate effect sizes. When I talk about calculating effect sizes, I mean this is particularly for the project that you're going to do, because you have your original article they're going to replicate, and they're going to report various statistics in their results, and likely they don't have the effect size reported. And because we want the effect size, so we have to calculate the effect size from what have been reported by the original authors, and that's why we need to do this in this way. But if we have their data, we don't do this. If we have the original data, we don't do this. We just calculate the effect size from the raw data. So here we're only discussing that calculating effect size from what's reported by the original authors, and we don't have access to the original data, so that's why we're doing things in the way that we're doing here. So now we have some descriptors, we have some statistical test results. Suppose this is the original paper that we're trying to replicate. How do we and because the authors did not report effect size, now we want to calculate how large the effect size is in Cohen's D. And now we use this package called Note. Again, if you don't have this package, you're gonna have to install Note with this line of code. So if you don't have this, you're gonna have to run this code to install it. then you have to load this package when you want to use the package, when you want to use the functions from this package. And there's a function from load that is called Cohen's D for independent samples t-test, and it takes in, for example, this function takes in a lot of descriptive data and an alpha level of 0.05 and the sample size, and the thing it generates as the effect size. You can see that it first describes the descriptives. They have a D calculated here. This is a D equals minus 0.62. And the confidence interval is minus 1.25, and the upper limit is 0.01. These are the descriptives, and this is the port standard deviation that the function estimates for a calculation of Cohen's D. And here, the good thing about this package is that it reports the effect size in a way that we are supposed to report them. So this is one way that we can calculate effect size and confidence interval with this package. And of course, we have many others that are mentioned in our guide. And just depending on what you have and what you need, you can choose to use some of them over the others, which might not be as applicable as to your cases. And now, if we want to calculate, if suppose these are not reported, the original authors don't report the descriptive statistics, and what's reported is only the t-value and the p-value. We can also do calculation from these two statistics by running another function from the mode package, which is called this one, and we input the t-value, the sample sizes here, and again we run this code. You will see that the function estimates the effect size based on our inputs. It's not gonna be exactly the same because these are not accurate numbers. These are just approximation. So for every packages, even among the packages that we mentioned in the guide, the results gonna slightly different a bit. It's gonna be slightly different a bit, but it's not. It doesn't matter as long as you report how you did the calculation transparently, and people can verify how you did it. And it doesn't matter if we get different results. We can always resolve that later. So the bad thing is that if you hide everything, hide your calculation, nobody can know how to arrive at the exactly same value as you did, and that's going to be bad for verification and the overall advancement of science. Suppose now we have the effect size calculated, and we have the confidence interval calculated, and now we are going to do a power analysis. How to do power analysis for an independent samples t-test. So again, with R, we have this package called power. First we load it, and there's a function called power t-test. This package is useful in the sense that power, where's my power? Okay, it's here. So this package also contains many other functions that we can use to calculate the power for different statistical tests. The only thing you need to know is you find the correct test that you're supposed to do power analysis on, and you input your data based on the required arguments, and then you just run your code and specify all the things that the function requires you to specify, and you run the code, and it will generate a power analysis for you. Now here, based on the effect size of 0.62, a desired power level of 0.95, two-sided independent samples t-test, we need 69 subjects per group to achieve this level of power, given the effect size that we have. So this is using like R for power analysis. Alternatively, for those of you who have downloaded Jamovie, Jamovie is a alternative but open open version of SPSS. As you can see, the interface pretty much is highly similar to SPSS, but much simpler, and I like it because it's cleaner. You have a spreadsheet where you can enter your data, you can transform your data, compute data, add data, delete data, and filter something out, like in this data toolbar. You can also conduct a wide variety of statistical tests in JMovie. And the good thing about JMovie is that it's also collaborative, it's open, and so that everyone can contribute their own knowledge to it. And in the background, in the backstage, JMovie runs on R as well. So when we conduct power analysis in JMovie, the thing we need to do is to install a certain module that's not innate in JMovie. It's implemented by other developers. But like you can see here, there are many modules here developed by various developers and used for different purposes. Like this one. This one is for mediation, and this one is for Bayesian analysis, and something for effect size and confidence intervals estimation. If you have the raw data, you can use this one to calculate effect size and confidence intervals, and some good modules about generating plots. And the module that we are using for power analysis is this one called JPower. Power analysis for common research designs. Yeah. So we install this module here. I already have this module installed. Yeah, now I have this module here. Suppose I want to calculate the power for an independent samples t-test with this interface. You can see the thing we want to determine is the sample size per group. We set a minimum effect size, interesting effect size of 0.2662 as our target effect size. We want a power of 0.95, and we want equal sample sizes between the two groups. And our alpha level is 0.05 in the two-tailed test. Now, the JMovie already generated the results for us. So it says that we need 69 subjects per group to achieve this type of power to detect this effect size. And the good thing about it is that it also provides a descriptive, some descriptions about this power analysis, which you can refer to when you report your power analysis in your manuscript. It also provides this reference table where you can see, so suppose the true effect size is above 0 and below 0.336, you're likely to miss it based on this power analysis. And suppose you have an effect, the true effect is between these two values, you probably can detect, but not with high power, with a power as high as 0.95. You also have this amazing power contour plot where the JPower module visualizes how things are going to change if you change different parameters, if different parameters change. So as you can see, if we have a fixed effect size, and as we move from fewer subjects to more subjects, our power is going to increase. And if we have a fixed sample size, the larger the effect size will be, the more power we will have. So this is the power control plot that is super understandable for you, I think. Yeah, it says that this module is for power analysis for very simple designs, and you can see that the designs, the support is really limited. But that should be enough for many cases as well. That should be enough for many cases, so it's still useful that you know that we can do power analysis here. And the last tool that we are introducing in this lecture is JPower. JPower is a software that was developed specifically for conducting power analysis. It has this very outdated interface, which for me it looks not as modern as JMovie, but the test the JPower offers there are more tests that JPower supports.
So for example, I want to conduct a power analysis for an independent sample t-test. I will have to first select t-test here for my test family. I want to select that it's an independent sample t-test. So it's means difference between two independent means, two groups. And this is matched pairs. That means an paired sample t-test. So for our purpose, we want to use this one. So if you have one sample t-test, you can choose this one. And just to make sure that where's my browser? Okay. We also have listed out a lot of guides for you to refer to, the videos how to use G-Power to conduct power analysis for different wide variety of statistical tests. So if you're not sure which test you should choose from the large number of tests G-Power supports, you can refer to this page to have an idea. It's also in the guide. So now we have a independent sample t-test to do. Type of power analysis. So as I just mentioned, what we want is a priori. That means determining sample size given alpha, power, and effect size. And the other names power analysis actually means that we leave one of the other parameter blank, and we want to determine that specific parameter based on the other parameters. So for example, sensitivity analysis, it's the this is the power analysis to determine how powerful, how sensitive our analysis is based on a certain level of alpha, based on a certain level of power, and based on the sample size that's already been determined. So we want to see how small is an effect size that this particular test and design can detect reliably if we conduct this sensitivity analysis. So for our purpose, we will use this a priori power analysis. We'll have to use a two-tailed test, and our effect size, target effect size is 0.62, and we want to aim at 0.95 power. We want equal sample sizes. So here the allocation ratio N2 over N1 simply means the relative sample size between the two groups. We click this calculate here, and it's going to show this graph, and it's going to show the results, how much power we have for this, and how many subjects we need for this kind of how many subjects we need to detect this effect size with this level of power. The important thing about doing power analysis in G-Power is that you have to copy paste this calculation protocol to your supplementary materials anywhere that's visible for others to check, so that others know what parameters that you use for this calculation, so that they can reproduce your calculation in on their own. So the key is reproducibility. So the thing that I want to re-emphasize is that we can see this tool is convenient compared with, of course, a bunch of R codes. However, it has many drawbacks that I'm not going to explain in detail. So whenever possible, please still stick to R instead of G-Power. Just only use G-Power when you find no solutions in R for your projects, because there are a lot of issues associated with using G-Power. Even though many people use it, we still want to encourage you to move towards more open, more checkable, more verifiable, let's say, tools. That's which is the R that we are we just showed. So back to the slides. So we demonstrated how to do power analysis for independent sample t-test. To summarize power analysis, the procedure of power analysis: first, determine the minimal effect size you want to detect. It can be the original effects that has been reported in the paper they're trying to replicate. So this is the choice that most of you is gonna be choosing. You're gonna go in this direction to and try to detect the original effects that have been reported in the original article. But just speaking more generally, how do we determine on the effect size that we're interested in? We can determine by based on pilot study. So suppose we want to conduct a large-scale study, but however, I don't know if it's worth it. We don't know if there's really an effect, so we can conduct a pilot to examine whether there's any preliminary evidence that there is an effect. So I get some estimation for the pilot study, and I will use that effect as my target effect in my in the main study. Yeah. Also, a more reliable estimation that comes from meta-analysis, where a lot of different studies are summarized, are quantitatively summarized, and an overall effect size for that specific phenomenon is reported. So because it summarizes many studies and supposedly correct for publication bias, this effect size is going to be more reflective of the true effect size in most cases. If we don't have meta-analysis, if we choose to not rely on pilot study effects, we may rely on the conventional or empirical benchmarks like the Cohen's d of 0.2 to determine our power. And then let's see how much power we want. In our projects, we want a power of to add this in the slides. So in our projects, we will mostly aim at a 0.95 power because we are aiming at we don't want to miss the effect, and we want to ensure that our replications detect the effects that is there. And then the next step is to determine what's the statistical test that we're trying to analyze. Is it a is it a paired sample t-test, an independent sample t-test, and what's the tailoredness? And then finally, we calculate the sample size using the tools that I just demonstrated. And then reporting power analysis. This is very important to report the analysis that we did in a comprehensive manner. So first, what tools you used to conduct power analysis. And since it's an a priori power analysis, you have to indicate that it's an a priori. The test that we're doing is an independent samples t-test. How do you get how do you get this target effect size? Is it from the original effect? Is it from a meta-analysis? Is it from a pilot? So most of you is going to report the original effect. So just report that clearly. And then the effect size measures was therefore entered into the power analysis with the following input parameters. And here you have to specify in the clear manner that what's the alpha level you input, what's the power level you aim to achieve, and what's the allocation ratio, what's the sample sizes for each of the conditions that for each of the between subjects conditions that you're planning, and then describe the result in the end. So basically, our replication our template where you will work on your replication extension project also has this picture, so you can refer to that when you write your manuscript up. And for your project specifically, you will first identify the analysis that test the main hypothesis. There could be multiple, so calculate the original effect sizes and confidence intervals. And based on the original effect sizes, conduct power analysis and at this level of power, and that will be your required sample size in your stage 1 report for your project. So if multiple effect sizes are reported, always aim to detect the smallest effect that it has been reported in the original article. The smallest effect that matters to the hypothesis of the original article. So for example, if we are trying to replicate this study, we examined whether there's difference in attitudes about psychology between those who attended Phyllis workshops and those who did not. We predicted that those who attended will think psychology more positively. So we sampled 20 subjects from each group and conducted an independent samples t-test to compare their self-reported positivity about psychology, which is rated on a scale of 1 to 7. We found that those who attended report a significantly more positive attitudes. T equals 2.57 and P equals 0.014. So we are replicating this study, and first we need to determine what's the effect size in this result. It turns out the effect size is, based on our calculation, is 0.83. And this is the confidence interval. Why do we need confidence interval? Because we are going to evaluate evaluate our replication result against the original result. And if we remember last time, in the last tutorial, I mentioned some criteria by some researchers that shows a forest plot. And you can, based on the forest plot, you differentiate between signal, inconsistent signal, consistent signal, that kind of thing. So we need confidence intervals for us to make the judgments. So a note here, calculate from means and standard deviation whenever these are available instead of from these test statistics, because they tend to be more accurate. And then conduct power analysis. This is the power analysis in R, and this is the power analysis with the G power. You can see that this, according to G power, we need 39 subjects per group, and according to this R code, we need also need 39 subjects per group. And then a final note, your sample size in your application shouldn't be smaller than the original sample size. If the original article reported an effect size that when you analyze it, you realize that you don't even need as many subjects as in the original article had, then at least you should aim at the original sample size. And in some cases, you can use this one rule of thumb. You just multiply the n you get with 2.5 and take that to be your required sample size. This method is referred to as the small telescope method by this researcher. And if you're interested, you can read this article, which I think is very inspiring and very helping to understand the whole thing about sample size planning. So yeah, that's the end of the tutorial. Yeah, if you have any questions, you can ask in the chat box or open your mic, and we can have a chat. Or stay until like 12:20, like the normal ending time of tutorials. So take your time to ask questions. If you don't have any questions, feel free to leave. And just know that we are always available on Slack. And just remember to tag us out when you ask questions, or else it's likely going to be missed for a little while.